start. So, as Simon has mentioned, we've had several of this week's sessions being devoted to solving more complex models and thinking about faster algorithms to solve them. And then few of these lectures, including these two, will be devoted to developing simple estimators. For example, the CCP stuff that I'm going to talk about, that essentially replaces the policy functions by using relative frequencies and drawing heavily on the strengths of large data sets. So why are we going through all these sophisticated algorithms if we can get these simple estimators? Well, the obvious answer is that we wouldn't be here in this classroom unless computation was costly, and in terms of human capital development and in terms of software. And so there's an issue about where you put your computational solution effort and where you put your estimation effort. Do you combine them? Do you keep them separate? Do you ignore one, look at the other? Those are all obvious questions. So these lectures, the ones that I'm going to give now, typically these lectures do either, and I'm talking about the week now, integrate the model solution into the estimation. So with the next, something like a nested fixed point algorithm, and Berto was explaining how that works in the case of dynamic discrete choice. Or they could exploit the data generating process, and by the data generating process, I mean take the model, get the equilibrium. The equilibrium is a stochastic process. What part of it do you observe in the data? That's called the data generating process. So takes the data generating process, figures out what is actually identified, point identification or set identification, for example, and then obtains estimates. And a third way is to take numerical estimates drawn from other studies, often done in macro, to quantify a model solution. And that often comes under the name of calibration. So each approach has its strengths and weaknesses, and the purpose of this lecture is not to debate that. Incorporating the equilibrium solution within the estimation algorithm gives you the maximum likelihood estimator, because you've got the distribution coming from the equilibrium. So that is handing you where is the maximum likelihood going to come from, at least in principle. And therefore, it's a way of getting asymptotic efficiency. And the fixed point algorithm that you use to solve inside the nest is obviously going to be useful when you're doing counterfactuals. Why do I mention counterfactuals? Why are you doing structural econometrics? It's because you want to talk about what would happen if you change the policy. You want to talk about, predict what would happen if you change some of the parameters in the model that you haven't seen yet. Because if you've already seen them, just run a non-parametric regression and you can get the prediction without any kind of deeper search. So moving on to this second method that I want to discuss today, if you separate the solution of the model from the inference questions, you naturally land into what's identified. Imagine your model produces an equilibrium. You see a bunch of data points out there that are produced by that model. You've forgotten about what model produced it, and you're asking, here are some data points. What class of models, because you're typically going to parameterize it, what class of models does it come from? You're asking, well, what parameters can we recover from this simulation? It's very loosely what we mean by identification. If you do separate inference from the model solutions, it's going to yield, at least unless you don't go through the Newton-Raphson follow through of solving the model once you've got consistent estimates moving forward from there. You don't do that, you're going to get less efficient, but much faster estimates. And you're still going to have to solve the model in order to do your counterfactuals, but not tons of times, only for as many counterfactuals as you want to do. So you're not searching over parameter space here, you're looking for estimates. You're doing counterfactuals to solve the, you're solving the model just to do a relatively small number of counterfactuals. And that's the sense in which, if it takes quite a while to solve your model, well then, why wouldn't you put your computing power there if you got a ton of data in order to do the inference? So calibration methods can dispense, sometimes do dispense, with the estimation step altogether. Just pull in estimates from wherever. Maybe you've got a few moments that you're estimating jam in as well. Even if you've got standard errors on some of the stuff that you're dealing with, there's the issue of, well, how do they interact? How do those, I'm going to call them marginals, interact with other estimates that you pulled in from somewhere else, because they might be correlated, of course. And so in that sense, disconnects the sample variation from the underlying probabilities. And when I talk about population, I'm not talking about the US population, of course. You know, if you've got the whole country, I'm talking about the urn from which you draw people in the US. Statistical probability. Okay, so too many times you hear about, well, I've got the whole population, so there's no standard error. It's rubbish. What they're trying to say is that we're drawing from a lot of people from the US population, 375 million or whatever it is, and that's why my standard errors are small. So those are the three methods, and as I've already indicated just now, how much data do you have, how complex is the model that you want to estimate, how sensitive are the estimates to underlying assumptions, what specifically is the policy question being looked at. Don't want to talk about it. I mean, yes, I'd love to talk about it, but not in 80 minutes. Okay, this is the kind of thing that we're able to go over lunch. The stuff that I'm going to talk about today is basically drawn from the lectures that I've put up there, and also probably the most relevant papers for today, for the first lecture of those two. So let's just dive straight into it. And to give us the framework, in other words, let's just bang, hit this with a model, start with a model, go from there. Everything's going to be under the null hypothesis. If you want to argue about the model, fine, let's do that, but not now. Okay? So generic model could be that time, discrete, it's finite or not. You're choosing amongst a bunch of J alternatives. So I'm just getting notation down. You've got discrete choices that are made each period. Pick one of them, set up so they're exclusive of each other. To keep it simple for now, we'll assume that the state space X is one of a finite number of things. When Whitney takes over in the afternoon, he's going to be talking about how to adjust the standard errors, or a way, but very promising way of adjusting standard errors when X is continuous. You know, there are a couple of ways of doing it, but I'll leave him to talk about that. But I will take the simpler route here and simply assume that X is finite, because that's going to means that there's only going to be a finite number of relative frequencies, etc., to compute. The epsilons are going to be are, but not yet, are later going to be type 1 extreme value. They're just going to be taste shocks that are individual specific. And we've got observations on the choices people make and the state variables that people have. This is a standard randomized utility model, McFadden, but it's going to be put in dynamic context, of course, by adding something called a beta. So the got a joint mixed density for how things move, and we're going to for this lecture impose the conditional independence assumption, which Burrell would have took you through yesterday. And the reason we're doing that, the main reason we're doing that here, is because we want to avoid a whole lot of integration. I'll talk about that later if we in the next lecture, maybe a little bit. So the conditional independence assumption is just saying, if you take the joint distribution of xt plus 1 and epsilon t plus 1, it can be broken up so that over here, the x's just move according to their state variable now and the choice you make, but not the taste shock. And the taste shock for each period only depends on the current value of the state variables. Where this one, of course, is the transition of the distribution of the state variables, and the G is just the conditional density of the disturbances. So as I said, we've got a discount factor, basically, because we're summing a bunch of utilities, and we don't want to be in a situation where if you go with one choice, it takes you to positive infinity. Next choice, next period, you go to negative infinity. How do you add them? Really hard. So let's bound everything. And so we'll do that by making sure that the expected value of the disturbances are not too big. And that way we can bound all this by geometric sum, because you've got this beta thing out there. And this is all kind of squeezed in to be finite. And so now we can talk about an expectation. The D's are going to tell you which choice you make each period. The T's are summing up utility as you move through the different parts of your life. You go ahead and maximize, get a social surplus function. Social surplus function being defined when you know the x's, but just before you know the epsilons. So you know you're going to take the optimal action for today when you see today's epsilon, but at this point you haven't quite seen it, and so you're asking, what is the expected value of the rest of my life when I enter the period before I see today's epsilon. And so the conditional valuation function, which is something that's used a lot in this kind of estimation, is then just defined as, let's look at the part that depends on the x, the current part that depends on the x. So we're leaving out the epsilon, and then look at everything else and ask, if I take action J today and everything optimal tomorrow, what do I get? And that's why it's called conditional. Well, I'm picking I see the X, I choose a J, go from there. I don't know whether that's a good choice of words or not, but too late to the literature. So the conditional choice probability then is just defined as, well, having solved this model for a given set of parameters, let's call that D optimal. Conditional choice probability is just, again, with the same information that I had up here, what's the probability that it'll be optimal for me to take an action today, given that I see the x's. So all I'm doing here is integrating it over the epsilons, once I know the d. So I've set this up as a, yes, go ahead.
I missed in the preceding slide why there's a capital P in the middle equation with the second part.
This part.
Yeah.
Good. So notice we're just defining something, and this is what the definition is. We take the utility that I'm getting today less the epsilon. So I'm leaving the epsilon out, and then I'm asking, what is the expected value of the rest of my life from tomorrow onwards when I'm integrating over what next period state variables are going to be, and also discounting that I don't get to the rest of my life until tomorrow, therefore I'm discounting it by beta.
And I thought that my life was small p and the welfare function was capital P. That's maybe where I got it wrong. It's capital P.
Capital B is the value of my life when I see X, but not my epsilon. And so that is the value of my life from now on, just before I've seen my epsilon. Here I haven't seen my tomorrow's epsilon. I also haven't seen tomorrow's X. So I've got to integrate over both. And I'm hitting it with a beta because it doesn't occur till tomorrow.
So small j are the states of the world.
Sorry?
The small j are the states of the world, like the possible realizations of the error or of the shock.
Okay. So just to move back a little bit. Here is how the shocks move. It's okay. Everyone has questions that everybody else is thinking. The state variables, the x's, okay? They are the things that determine the state of the world at any given time. It's going to be one of those. It has a transition function that looks like this, from period to period. The epsilons are taste shocks. They affect current utility. They are IID, well, not quite IID, but set up like this. They do not depend on the past. They only depend on the current value of the x. Okay? Call me up whenever you want. Okay, what I've described is the is an individual optimization problem. Let's switch to games for a minute. Think about what you're doing in a non-cooperative Nash equilibrium. You are best responding to everything else that's going on, whether it's driven by nature or by other players. And so that means you are still solving a dynamic programming problem. So in this case, the x's now, of course, depend on the state variables of everybody in the game. My capital, my rival's capital, blah, blah, blah. Okay? His capital will affect my capital differently, of course. Sorry, his capital will affect my payoffs differently than my capital will affect my payoffs, obviously. Each of these guys is making a choice. This is a set of choices by everybody. Here are the set of choices by everybody but I. We've got a transition probability that depends on state variables of the whole industry today, choices of everybody else today, what happens tomorrow. And so we can talk about from this, what if I make choice J, everybody else does their thing, and the state variables are what they are today. That will determine what happens tomorrow. Now, as far as I'm concerned, or Mr. I is concerned, I'm thinking about my big utility. So now I'm actually using a big U. That depends on state variables of everybody else's actions, what I choose. This actually works. Can you see that? Good. Here's the utility that I get, current utility in this game setting with my epsilons going to be the IID. Let's keep it simple, same as before. We're using a conditional independence assumption. Notice my little shock doesn't depend on anybody else's taste shock. Notice that. I can't learn anything about the other people from looking at my shock. Okay. And I'm not going to see these guys' actions or their taste shocks. And then I'm going to be thinking about, well, what's a Bayesian Markov perfect Bayesian equilibrium in this setup? So all I'm going to be thinking about is, given my actions and my choice, given the state variables, what is the probability of my choice under I? I'm going to be thinking about integrating over what everybody else does. Okay, so I'm going to be setting up a conditional choice probability here in exactly the same way as I'm doing it in an individual optimization problem. And everybody else, for me, is, well, I don't know what they're doing, so I'm just going to be integrating over their choices and forming that as a probability. And so we can then define the Bayesian equilibrium, or to put it another way, the individual optimization is solving this. If we're in an equilibrium, and these are the equilibrium choices, then the expected utility that I get from today, just today's expected utility, is just going to be what I would get if everybody else does a particular action, and then I'm integrating over all their actions. Okay, so here's my utility function. Here's my utility function. I don't know what everybody else does. I will integrate over what everybody else does. That'll be my expected utility that I get when I see state variables xt and I take action j. Okay? And if I define the transition function as, well, I'm going to take action j. Here are my, actually, it should be here. This shouldn't have an I on it. Excuse me. I won't try and rub it up right now. Here are here's the state variables for everybody. How is this transition going to move when I take action j? Well, I'm taking action j. Everybody is doing their thing. That's going to determine what fj is, that this probability transition is. But I don't know what they're doing, so I have to integrate over their probabilities. Now, if you do that, well, then we're right back to the individual optimization model. Yeah.
So we're living in a world where you can't observe what the other players are choosing?
Not at the time, only afterwards. Now, afterwards, it doesn't matter because all you care about is the state variables. So to be a little bit more clear, because the question is for everybody, you don't see what other people are choosing. Of course you see what rivals are choosing. What's going on here? I'm extrapolating.
That's what I was saying.
So what's going on here is that I'm thinking about inventing the next model car. My rivals are thinking about inventing the next model car. The cars come on the market, and then we go from there. I see later what my rivals have done, like the very next period, but it's kind of like too late. Now, if you're writing a paper, you don't generally show all the drafts to everybody in rival schools. I don't think.
Right.
So that's what I'm saying. That's what happens in a non-cooperative game. People are making simultaneous decisions. They are not actually they're not seeing the actions in that straight away. They have to take their action before they see other people's actions. That's really what it
Are we
means.
like allowed to construct beliefs? Or
Sorry?
Are we like going to be constructing beliefs or?
That's where these probabilities come from. They're because we're talking about a Bayesian Markov perfect equilibrium here.
Okay.
So this is a yes.
Plus the little cross up there that's the bar with.
Ah, yeah, that would be a good idea. That'll help explain everything, right?
So we can see the.
Yeah, that would be good. Thanks.
Just.
I'll move this guy.
Just a little bit to left.
It's left, you reckon?
Okay.
Is that better? Yeah, sort of. Okay. Good. Yeah, it is better. You're right. Much better. Okay, let's start again. No. Okay, I handled the question down at the front end, right here in the corner. Yes? Yeah. Good. And you're all clear about that. Move on. Because I'm going to go back. No, not quite.
First of all, like there's any of the templates, right? It's like so for every time t, first the state variable xt is updated, and then given the xt, the absentee are updated, but I can only see my own absentee, and then everybody do their action e together, then everybody see other people's action. You're moving on to the next.
That's correct. So you walk out of the last period. As you walk out of the last period, X gets updated. Beginning of the next period, you see your own epsilon. Each person sees their own epsilon privately. They all see how the X is updated. They all make their decisions for this period at the end of the period, etc. Which is what you said, I believe. Uh-oh.
Press the slide again.
Yeah, like that one, for example. Okay. So let's go back to the individual optimization problem. Starting point for thinking about how to estimate without solving, but at the same time, respecting the fact that the data generating process comes from the equilibrium actions of each of the players. So it's almost the reverse of the way you might think about doing policy stuff. When you think about building a model, you kind of introspect a lot, and then you think, okay, I'm going to build equations here and here, and for optimization, technology, and all this, and then I'm going to solve it. So there's a lot of introspection. And then at the end of the day, you get the equilibrium outcome, and it's like, oh, here's what happens, sort of thing, if I said to do that. This is going the other way. You start out with, here are the data. How could it have been generated? And I'm going to make some assumptions about how it could have been generated. For example, everyone's going to be an optimizer. Well, if you don't want to make them optimizer, make some ad hoc assumptions about what they do behaviorally instead. Even better, come up with some axioms to explain how they behave if they're not behaving optimally. Okay, so we'll go with a simple case where people are Bayesian and people are optimizing. So you start out with the data. You're thinking, okay, these guys are smarter than me, because they were spending more time on their problem than I am spending on their problem. They're solving life cycle problems. I'm just trying to write another paper. Okay? A little bit of difference there. So we got the difference between, and we're asking, how do we use what we see in the data to get back at what the parameters must have been that were driving their decisions? That's what we're doing. So you got the difference in the value, the conditional value functions. Well, if you are asking, what is the probability? What's the conditional choice probability? Well, why not just add in a, say, a norm choice, the jth choice in here and here, as opposed to these, right? Because obviously probability is sum to 1. Or to put it so the last probability is 1 minus all the others. Likewise, when you think about valuation functions, well, if you added or subtracted a constant from all of them, does nothing. So you got an indicator function here that says, well, this plus this must be less than these two for everybody else. In fact, since it's a weak inequality, k, you don't even have to have k not equal j, just for all k. And so that's equal to this, just writing it out. And just integrating through, that is equal to this thing. In other words, define the derivative of the cumulative distribution function by cumulative distribution function for all the x's, for all the epsilons, given the x. Okay, different choices. Take the derivative of that thing. This is what the conditional choice probability is equal to. Okay, so let's notice a couple of things here. This is true for each of the j's. Let's not worry about the x's. Hold x fixed. Okay, for any given x and any given t, move those two, kind of irrelevant. You got theoretically cap j of those, but really only j minus one of them. And over here, you've got, well, how many of these have you got? Once you get rid of the x's and the t's, you've really got, again, cap j minus one of the differences. Yeah.
What's the inversion again for that inequality? Epsilon k is less than epsilon j plus the difference.
This one here?
between these, yeah.
Yeah. Okay. This guy is taking an optimal action. Okay. Now, when is he going to take an optimal action? Well, when, remember what the definition of the conditional valuation functions is. It's a little bit hard because I only gave it to you about 2 minutes ago. But basically, it was it. Slide back. Here it is. When is this plus the epsilon biggest for the j? Because that is, when that's the biggest for the j, you will take that j action. Okay? Now let's go to this one. And the only difference here is I got a triangle. Now, where's the triangle come from? I'm just subtracting the big J off both sides, or here and here. All right, where I not really both sides, but if I had this over here and had this here, Bj plus epsilon Bk plus epsilon k has to be less than Bj plus epsilon j given x and given t. That's what makes this option action optimal. And then I'm integrating over all the epsilons. Okay? Now I am
What is big j?
wait, let me finish. And then what I'm doing is taking off big J from from here and here. Okay?
Yeah, sorry, I'm just confused about what big j is.
The big J up here is B capital J, which is the action, the value, the conditional valuation function associated with the last action, J. It's not action 1, action 2, action 3, it's action cap J, because there are capital J actions. Okay? Good. All right. All clear? Yes? Good. Don't worry if I go like this. It won't explode. It's better to get it out so that it's concrete. Sort of builders. All right. So I kind of got to this point where I was saying you got as many delta V's as you've got P's once take into account they sum to 1. And so do they invert? And that's where obviously I'm going. So let's set up something else. Something that I almost did before. this in the previous slide. Let's define these deltas up the top. See that? And I'm going to think of a McFadden random utility model. Static, no x's. And all you're going to do is get a utility which is equal to delta j plus epsilon j. Okay, that's the model that I have in mind here. And you're going to pick the biggest, the one that gives you the highest utility. So do you pick delta 1 plus epsilon 1 or delta 2 plus epsilon 2? You just choose the biggest, all right? That's the underlying thing. Because after all, we're thinking about proving this for all x and all t. So if we define this q that way, then just from the previous slide over here, it is the probability of picking action j in this static model with these payoffs. Okay. And so that's how we're going to define this model. That's how we're going to define Q, right? Well defined. If I knew what the cumulative distribution function of G was, I need that cumulative distribution function of G. See that? And that's obviously going to be in almost every application you do, the product of all these type 1 extreme values, where each type 1 extreme value is the independent shock you pay off for that particular action. All right, so this inversion theorem basically says that this thing does invert. And so you can write down the delta V's in terms of if you know the distribution of the joint distribution of the Tay shocks, if you know that, you can write it down in terms of the conditional choice probabilities. And that, of course, is going to give away the ball game. All right. So to get to that point, I want to define this correction term, this psi function, which is just the difference between a social surplus function and a conditional value function. Again, it's notation, but it's going to be notation that helps us give a representation for not just the conditional value functions themselves, but also the utilities themselves without any further assumptions. Okay? So in stationary settings, you're obviously going to drop the T. Why do I call it, or why do we call it a correction? Well, intuitively, if you just took action J without seeing your epsilons first, in other words, you did this non-optimally, coming back to whatever to the time sequence of things. If you did this non-optimally, well, then this is what you get. You get your conditional value function plus the unconditional. When I say unconditional, it's you don't see the epsilons. You get the expected value of the epsilons conditional on the state variables. So if you commit it to J beforehand, you get this loss, okay? Just be the difference between these two things, which is obviously the difference between these two things. And if this thing, for example, had a value of 0, which it doesn't with type 1 extreme values, I understand that, it's 0.7577 or whatever. But if it was standard normal, it would, then it would be exactly this term. So that's just the intuition for why it's named that way. It plays an important role, that's why I have to give it a name. So what is this thing? Well, imagine there are a bunch of choices in here. some of these are nested in this kind of nest, and the others are any old generalized extreme value function. Okay. Well, then the correction factor would just be equal to this. So in other words, if there was no nesting anywhere and this wasn't there, well then this thing would be equal to 1, this would be equal to 0, and yet the correction factor for the type 1 extreme value would just be gamma minus log p, where gamma is 0.577, Euler's constant. So you can see straight off that it's dead easy if you were doing either a static model or a dynamic model in this kind of world to have nested logic with various nests of So that's just an example. So I want to now talk about why or how this correction factor is used. Start out with the conditional value function. We've already defined it as equal to the little u plus the beta of x periods b. And you can see why I'm happy to answer these questions, because here's the same formula again that we're talking about that I wanted to go through before. And we could imagine that we could, instead of having bt plus 1, we could just say, well, okay, that's equal to little vk plus epsilon, because when do we go back and define this thing? This might be a little hard. I wanted to, yeah, here we go. No, that's not the one I wanted. Here we go. This is the one I wanted. Look at this. Big V is equal to little bj plus the correction factor. Okay? That's true for all j and all x. So now, what I want to do is substitute for bt plus 1, little v k plus correction factor for k. Here it is. Okay. And here. And so I get this. All right. Fine. But now for this guy, we could just keep going, because after all, substitute, put k's in here. See this? Put k here, here, and here. And then put it for t plus 1. Put that down in here. Induct to the end. All right? Could have put in any k. All right? So I could have expanded this out in terms of, look what I'm going to get. I'm going to get u, j's, and k's, and God knows, lots of u's. Mess of linear combination of u's. This is all linear, of course. Mess of corrections. Again, linear mess, just putting them together. Adding them up, and then I get my conditional value function back. So think about what that really means. I said, even showed you what this term is. Get some probabilities here. You've got one parameter here, you've got a number here. Hey, that's almost a number. Plug it in here all over the place. This transition function is right outside the model. That's what the conditional independence assumption allows you to do. Get this in. These are just numbers after you've estimated them. Now you're left with a bunch of u's, linear combination of u's, and that's what your little v is. Okay. What are you exploiting? I'll get you. What are you? I'll get you in a minute. What are you exploiting here? The fact that these guys have already solved the model. You assume that front end. I did anyway. And so you're taking their optimization and saying they've already solved the model, and I'm going to exploit the fact that they've solved the model in order to do inference. Now, if they haven't solved the model, okay, we'll build a model in which they follow some other behavioral rule, and then we'll talk about it. And hopefully it's not an ad hoc behavioral rule, otherwise I might get a little bit pissed off. But that's where we're going here. Yeah.
A different way to consider the correction term is that as kind of the distance from the expectation. So when you have capital B, that's the expectation. So it's, but you can get a closed form expression for that, for the distance to the expectation.
Yes. So here I've just told you, this is what it happens to be. I haven't told you how I got that yet. I will. But yes. And it is definitely this distance. Here it is. Okay? That's how, as you see, that's how it's defined. Yes, as I said, I've said this is what it happens to be. Haven't proved it yet. I will. All right. So that's where we're going here. Yes, yes, sure.
So the idea for running this correction term is basically when you're tracking up on the data to one.
Yes.
To adjust for any non-optimal behavior that.
No. These guys are optimizing. We are the befuddled econometricians, PhDs and all, that are trying to understand what parameters they used when they were optimizing. And so we are taking it for granted that they know what they're doing. And we are saying, why did this person do this? It's a detective story. And when we see those correction factors there, those correction factors reflect the fact that they were optimizing, looking at the epsilons that they have when they made their decision. And we're saying, okay, well, there are the X's and they don't look that great. And yet they made that, the conditional choice probability is not zero. Why not? Why did they make those choices? It must have been that their epsilons were really high, that particular epsilon that lead that choice. Okay? That's the sense in which the taste parameter, this taste shock, is playing a role. It's sapping up what we can't explain, sopping up, there we go, with what we can't explain with the X's themselves. And that's always going to be the case in all of these kinds of models, of course. Okay? All right. So I went through what happens if you put the case choice. I then said, hey, you could have put in any choice. What do I mean by that? Well, what I mean is that when I'm thinking about this, what sums to V? In other words, if I shift the VJ, if I shift the VJ from here to here and put a plus sign, so that I've got equal to big V, how can we generalize that? Well, any linear combination such that the weights sum to 1 will obviously deliver big V. Notice they don't have, the weights don't have to be positive, they could be negative, and I'm going to give you an example to show what that is useful. Okay. But providing they sum to 1, we're good. Notice they can depend on X, obviously, and they could also depend on T, of course. All right, so the basic point is, once you take that into account, you've got weights, these weights that you choose. Weights that you choose. Let's keep everything bounded. And that gives you that the conditional value function is going to be equal to current utility plus future utilities plus these correction factors with weights and X transiting according to the combinations that you've picked. Okay, so over here, if you pick the jth weight, if you pick the jth action first, which you're doing, well, then that's going to push xt plus 1 according to your jth choice. In the future, will you start out with whatever the distribution of k was that you've reached there using the weights that you've got, and then you ask, well, where are you going to go next time? Okay, I'll get you. So you could obviously set this up as some kind of Markov matrix, but I haven't done it yet. Yeah, go ahead. I think
Can you clarify what the weights are again?
Say it again.
Can you clarify what the weights are again?
Yeah, sure. Let's go back to this slide. What I did here was that I put in a kth weight. I said, yeah, I put a weight of 1 on the kth choice. If I put a weight of a half on the kth choice and a half on the weight of the half weight on the k prime choice, well, then the omega for the k would be a half, and the omega for the k prime would be a half, and all the others would be 0. I could have put a weight of 3 on 2 for the kth and minus a half for the kth choice, still good. These weights defined over here, these are defined, anything that satisfy these two criteria. Got to be finite, got to sum to 1. Okay? So you pick them. And that obviously means there are lots of ways of picking them. And there is an issue of, well, which way should you go? And working out the asymptotic matrix for that is not actually formally done, although there's a fair amount of intuition about what works and what doesn't. And it's going to be specific to each problem. All right. I'm going to get back to this question of where do these correction factors come from? And the way I'm going to do that is we got a representation of that value functions here. Now, what's identified out of this model? Okay, haven't quite reached where we are, but let's see what's going on here first. Suppose the optimization model fully characterized by what is t, finite or infinity or whatever. What is the discount factor? What is the transition for the state variables? What is the distribution of the unobservables? And what does the systematic parts of the current utility look like? Okay. So you've got a bunch of a bunch of observations. What's going to be identified, say, if you had what I'm going to call a synthetic cohort, basically a bunch of cross sections that cover all ages and actually all choices, because it's going to be big enough so that all choices are going to actually be reached. It's just a question of how often. We're dealing with choices that are only reached once or twice. We're back to the newspapers. You know, we don't have a good probability theory of those kind of stuff. So here's our optimal decision rule. Okay. And by definition, it's equal to this thing. All right. Now I'm just subtracting these j's, so I get the deltas. Okay. Still our optimal decision rule. But this thing inverts. But we have an inversion theorem. Depends on the conditional choice probabilities. And so once we've got the conditional choice probabilities, once we've got our G is 9. Okay. That is what the optimal decision rule is. Okay. Notice the optimal decision rule depends on the state variables and the epsilons that you draw. So it's actually important to distinguish between what I'm going to call a policy function, which is this optimal decision rule, versus the conditional choice probabilities, which integrate out the epsilons given that people are behaving and recognizing that people behave optimally. Okay? And the reason I emphasize that now is because I've seen the papers in Econometric that don't get that. And so it's important to understand this is identified straight off, and notice what's necessary or what's sufficient to identify are these conditions on what the distribution is. And we'll go back to what you can identify about G in a minute. Okay. Short answer, nothing. So let's go to the correction value function correction here. That by definition is equal to the difference between the surplus function and the conditional value function. The value function itself is just a weighted average of the conditional value functions plus the epsilons integrated, the right epsilons integrated in their right regions. What do I mean by right region? Here we have the joint distribution of the taste shocks. Sometimes you're going to make little j, sometimes you're going to make little k choice. Optimally, so let's put that in here, because you're making optimal choices. And when you do that, you get the epsilon for that optimal, that's associated with that optimal choice. So if we sum this with these guys and sum for these, okay, you get big B. And if you take this VI and then pull it outside, notice this depends on J, not I, well then the probability is just sum to 1. Okay. Sorry, let's keep moving here. But let's look at this. Vj minus Vi is just the Q stuff, which depends on P's. Let's look at this guy. Let's expand out. Epsilon K's, we've already seen this from previous slide, that just depends on P's too. So, given X, given T, given G, this thing just depends on the conditional choice probabilities. It's identified. So that is the beginning of the answer. Where do we get this stuff from? Notice that we need the G's. We need the conditional choice probabilities. The G's are used to get the Q's back from the inversion theorem, and then the rest is just numeric. Okay, so that's the sense. That is why the size are also identified. Okay. Look at what I've used here. I haven't used anything about beta yet. So, you know, when we're talking about how we define the V's, wherever it was, sorry, maybe I won't go back and I'll just leave that for you to think about. Haven't used anything about the betas yet. Okay. I'm just assuming we know the G's in order to pull all this stuff off. All right. What about the current payouts? Yeah, this question.
Can we go one thing back?
Yep.
So how should we think about the integration? This part, yeah.
Yeah, sure.
So you have the optimal policy of J, and then you integrate out the epsilons, right?
Wait. Notice for J here, we've got a 1 here when J is optimal and a 0 otherwise. So which epsilon are we picking out? That's the way to think about it. We're summing over all the possible epsilons and we're picking out epsilon little j only when this is 1. And when is it 1? When the guy's behaving optimally. And so we're picking out epsilon 1 when action 1 is optimal, epsilon 2 when epsilon 2 is optimal, and in that way, getting the expected value of the taste shock or the expected value of the stuff that I can't explain by my X's, given that the guy is behaving optimally and given that he's making these, given that he's making these choices.
So it is an expectation, yeah.
Yes, because look, here's the here's the epsilon that you get, and we're integrating over the, notice ET is the joint of the epsilons. Fair enough? Good. Clear? Yes, one more question, I think.
So why do we then require the weights at all for this identification?
Why do we
require weights?
require the weights? The answer is not yet. I'm just saying this is why all the sides are identified. Okay? I said, yeah, we can get the policy function. Actually, I'm not going to use that. That's a cheap shot at some of the stuff that's already been written. This one, we're actually going to use. Okay? Now, although there's still a little bit of a question as to why we need all the weights. We'll talk about that later. Okay. We're going to get the U up here. And what I'm going to claim is that the representation result for the value function implies this for the U's. And let's figure out what it implies first, and then we'll worry about how we got that, because it's really cheap, easy, I think. Little u is equal to a little u1. So another way of thinking about it is uj minus u1. Now think of a static model for a minute. You only identify differences in utilities, right? Obviously. And then there is a correction term here, okay, to reflect whether these are optimal or not. And then there's some stuff that apply to everything in the future. All right? So it's almost like the following. We're looking at, where are we? This guy. I already went through this one. Now let's take it for the first action. So Vj minus V1 is going to be equal to, go just a little bit further back, Vj minus V1 is equal to V minus V, that's 0, psi j minus psi 1, okay? So moving on, Vj minus V1 over on the left side is going to be psi 1 minus psi j, actually psi j minus psi 1. And then over on the right side, we've got uj minus u1 and all this stuff related to these kappas, where in one case you start out with action j, and in one case you start out with action 1. Difference that guy for any set of omegas. So I still haven't answered your question. I will. So we go here, and that's what this does. Here we got the j minus the 1, okay, in the kappas. And here we got these correction factors here. And here we have little j, uj in terms of u1. In other words, if you start, let's start putting some norming stuff on this. Why don't we fix beta at 0.9? Terrible assumption. Because what it seems to suggest is that beta is like the law of gravity, some universal constant. Crap. Beta applies to each of the individual models that we're looking at. And, you know, we're not trying to explain the world here. We're not Newton. Well, I'm not anyway. And so we haven't reached that point of that universal constant. And so why would you want to fix that parameter? How much are people looking forward in this kind of world when there's a whole bunch of other factors which you're ignoring altogether? Okay? But But in any event, I do it too. Guilty as charged, Your Honour. Like all those other flippers in the Trump case. Set beta. Okay. Norm one of these guys. Norm it at 0. Okay. So all comes out. All right, this is all 0. Look what we got here. Correction factors over here, correction factors over here, numerical stuff that's calculated from the F's and stuff. We're done. That is a unrestricted estimator of the utility that comes out of the model, just exploiting the fact that these guys are optimizing, and therefore we can just exploit that like crazy when we're doing inputs. Same kind of thing in a stationary model, and you can write it down in matrix algebra. Let's move on.
On Monday, John had a model where beta was excluded from the process.
Yep.
And I'm just wondering, like, could we accommodate that kind of thing here? Or, you know, we don't know beta, but we know that beta is this kind of thing.
All right. So if we're going to think about having beta in here, let's make beta a function of x. Okay. Now, what I'm going to talk about in a minute, I think, is that this model is actually, we can do it now. This model is exactly identified the way I've set it up. Exactly identified, because you've got as many little u's as you have conditional choice probabilities. Takes a little while to do the counting, but basically think for each t, for each h, you've got j minus 1 u's and you've got capital J minus 1 p's as well. Okay, so there is many of each. So with respect to Arnaud's question, if we're going to make beta depend on something and then we're going to estimate it, well, then we have to make functional form assumptions about how these little u's are linked to each other. Well, can we do that? And the answer is yes, we do it all the time, because often we'll say, well, u is a function of x, x can take on the values of 1, 2, 3, 4, or 5, say, and then we're going to say u of 5 is equal to alpha times the number. In other words, we're going to make a linearity assumption on how the different values of x affect utility. And right there, we get 5 extra restrictions. And depending on how we're going to then estimate how dependent we are going to make beta depend on x, we pick up some restriction. We get some restrictions that we can exploit there. Okay, so there's a trade-off here. Let me say there's another aspect to this, which relates to the disturbances that I was talking about before. I went through the nested logic case, and there was a sigma there because we wanted to look at this correlation between the nests right here. Okay. Well, do we know the sigma? Well, typically we don't in these kinds of models. We want to estimate it. So if we're going to estimate that thing, well, then we had better put an assumption on the functional form of this in order to be able to get to estimate an extra parameter over there to get something about the G's, because the G's are clearly important in coming through here. We talked about what the correction factor was. Okay? So there is this trade-off between where you put your restrictions. And so here I've given you, intuitively, but it's proved, a set of necessary and sufficient conditions for point identification. It is one set. You know, you could obviate, and the reason I give you that set because it's an intuitive set, easy intuitive set to explain. But obviously you can make these trade-offs. Put assumption, you don't want to make so many assumptions about your disturbances. Well, okay, put assumptions on your U. Here is your unrestricted version. You've got what I'm going to call minimum distance estimators from this. in a minute. And then we're going to get extra restrictions that come from perhaps putting assumptions on the use. I'll move on for now. Let's talk about the unrestricted estimates I've already given. Okay, just by plugging the hats in, because now relative frequencies, kappas form from these relative frequencies go from there. Okay, just putting in the sample analogues for each of the things that I've already talked about to identify. All right, and if we weren't going to put any restrictions on it, well, these are maximum likelihood estimators. These are maximum likelihood estimators. Invariance principle. This is a maximum likelihood estimator, which means that the only way you can get more efficiency out of this kind of model is to make functional form restrictions about the use. Okay, if you're already specifying the G's. And there's not an argument against making functional form restrictions. We do it all the time. But we would like our functional form restrictions to have some institutional basis if we can, or engineering basis, something like that. Okay. In practice, we may, as I say, make functional form restrictions all the time. These are the kind of assumptions that we make. Maybe this is linear. Maybe this is degenerate. Maybe we know the law of motion. Okay. So this is a kind of thing that you could do. So one approach, get the unrestricted estimates that I talked about just a minute ago. Now, impose a functional form assumption on the use. Go ahead and minimize quadratic. Notice. So if this thing was linear, this would be linear and quadratic. Obviously, a closed form solution. Just solve it straight off. All right. You could do something else. Because really what we've worked through is how you identify, and then given you identify, there are a bunch of different types of estimators that you can use. Type 1 extreme value, suppose we just do it this way. Well, let's put the current utility in here, and this H, I'm going to call that a correction factor, a dynamic correction factor. Because the guy is not solving a static utility function, in which case the H's would go away, vanish. You're solving a dynamic problem, in which case we're going to maybe put a beta on or estimate it or whatever. So we could do that here. And if you did that, you just put in this correction factor for each of the choices, go from there. Notice that again, this is a number, okay? I want to emphasize that. This comes from kappa being computed from the F's previous that you've already found values from, correction factor computed with type 1 extreme, we've already got it. Beta is a number. Put that number in here and solve the logic, okay? To get the answer. Get your thetas. Yeah.
How do you construct an example on both sides?
Yeah, let's go back to wait. Yeah, right. Question is, how do we construct the x's or the psi hat? Okay, I want to pull back. Yeah, we got it. What was it? Substitute representation. Here we go. Here's the psi hat for a nested logic. Now, admittedly, there's a proof behind that, and so I'm not going to do it now, but you know where to go. And that's for nested logic. So for regular type 1 extreme, of course, this sigma is 1, and so it's 0.577 minus the log p. Actually, this thing goes when you do the construction, not surprisingly. So it's really minus log p. P is just a sample analog, plug it in, log, done. Okay?
So 18.
Oh, sorry. 18, yeah. And you're asking,
Be just general form.
sorry, where are we? What are you asking me?
So if we're not in the extreme,
Yeah,
then we could just use this form, doesn't use the first Q.
absolutely right. So just a couple of things on that, just to follow up. We would use the inverse Q there, okay? But then you still have the correction factor, but we showed that that correction factor, gone way too far here. I want to find the correction factor to be identified. And I proved that somewhere. Here we go. Yeah, here we go. So we're relaxing the type 1 extreme value. And so now we've got the Qs, and then we get a correction factor from this formula. Okay. So in terms of the numerics, not a problem, but then you've got this trade-off between what kind of functional forms do we put over here versus what kind of functional form do we put over there. That's something that could be explored much more than it is now. And the reason why it's interesting to think about that is because while these different representations are observationally equivalent, I'm going to stop in a minute. While these representations are observationally equivalent, they are observationally equivalent for the data that we have, for the regime that's in the place now. They are not at all observationally equivalent for the counterfactuals. And so we really do care about this because we want to get at what those counterfactuals are going to be. All right. Almost done. Or we could do these simulated methods of moments estimator. Worth pointing out, because here you're going to simulate paths straight off the conditional choice probabilities, and coming to your question, we can simulate off the P's that don't make any assumption about the G's. Where we need that assumption is right here. And that is the tricky part. And that's where we might want to think about playing stuff with stuff. Because obviously, given this stuff is so simple to estimate, the issue is how do you want to play with different kinds of specifications before you commit to solving the model? All I've done here is shown how the simulator stuff stitches together. You guys should know how to do this by now. So I'm going to stop